have this opportunity to share with you guys some of our latest progress and efforts. So one of our major pursuits is to build better open models. And we believe in democratizing intelligence. With open models, you can deploy anywhere. You can be on your local servers, you can be on the cloud, and you can access every single bit of the weights in the model instead of just using a black box. And this is one of the slides that I took from Jensen's talk earlier this year at CES. So as you can see, open models are quickly closing the gap with proprietary models, and it's reaching the frontier. And we believe that with better and better open models, we're going to make intelligence more accessible to anybody in the world, in every corner of the world. But open models cannot be just open. They have also to be great. So in this talk, we're going to discuss how we make open models great. So as we know, scaling is a primary driver for a lot of progress, maybe all of the major AI developments that we have witnessed in the last few years. And here we're going to discuss how we scale our model in different dimensions. So on the left-hand side, the first figure you see here is kind of the standard scaling law. So on the x-axis, you have the log of the number of training tokens, and on the y-axis, you have the log loss. And as you scale the number of training tokens, you get a lower loss. But here the point is, we're not going to just scale the number of training tokens, but we also want to improve the token efficiency. Meaning that we want to move this curve to the left-hand side so that we can achieve a lower loss, a much lower loss, using the same number of training tokens. And this can be achieved by having better architectures and optimizers, as we'll discuss in our later slides. And the second scaling dimensions that we're very interested in is to scale the context length. So as you can see in the second figure, if we increase the context length, then we can have a much higher accuracy in terms of predicting the token loss at a given position. And this means that we can increase the capability of the model to achieve more complex tasks by increasing the context length. So this is the second scaling dimensions that we're going to talk about. And the third scaling dimension is the number of agents. So we introduced this new learning paradigm of agent swarms, where we don't just rely on a single agent, but we also orchestrate a swarm of agents that can accomplish the subtasks in parallel so that we can increase the task complexity. And we can translate all of this into the language of agents. So if you look at token efficiency, it's mostly about having a stronger prior so that you can have more efficiency when you do agent RL to search for a better solution. And when you think about long context, it's mostly about increasing the context length so that you can have a longer running agent. It can probably run for days or even weeks or months to accomplish more tasks, more complex tasks. And for agent swarms, it's another dimension that add to it. And at the end of the day, we're going to have a swarm of agents that each of them have a super long context, and each of them have a very strong prior for us to search in this entire agent RL system. All right, so we're going to start from token efficiency. So this is one of the most classical figures in the history of machine learning. Right? So it's taken from Kaplan et al. And it basically says that if we scale proportionally the number of training tokens, the model parameters, and also the amount of compute, we can get lower and lower loss. And this is one of the major breakthroughs that the entire community has achieved in the last few years to get better intelligence. But here, what we're interested in is to have better and better token efficiency. And here's the thing. So one thing that I would like to emphasize is that token efficiency is not just about efficiency. It's actually also about improving the upper bound of intelligence. So here's why. So suppose you have say, 50 trillion tokens, 50 trillion high-quality tokens, and then you apply this new optimizer, maybe the Muon optimizer, and then all of a sudden you have a 2 times token efficiency. So it means that it's almost like magic that you get equivalently 100 trillion tokens. And nowadays we are scaling towards the data war, and we're hitting the data war, and the amount of high-quality data is quite limited. And if we suppose that it's a constant amount, then we increase the token efficiency. It means that we're going to get better intelligence out of it. It's not just about infrastructure efficiency. It's about better intelligence. So this is why we spend a lot of efforts in this aspect, because it's going to push the frontier of intelligence. And Muon Optimizer is one of the things that we have heavily invested in since last year. So it's a second-order optimizer. And basically, every single gradient update is transformed in a way that each entry is orthogonal to each other. And this is very different from the traditional Adam optimizer. And if we implement this optimizer properly, you can get a 2 times token efficiency improvement. So we are the first work. We published the first work to demonstrate that Muon optimizer is actually scalable for LLM training. And these are 2 key techniques that we employ to make it effective for large-scale training. So one of them is weight decay. It is critical for scaling to larger models. And the second is we want to ensure a consistent RMS updates compared to Adam. So we have this adjustable coefficient that is applied to each update, so that the resulting RMS is going to be comparable to Adam. And to make Muon memory efficient across all these NVIDIA GPU clusters, we also develop a distributed Muon optimizer implementation that partitions the states across the data parallel group, so that we can have a very efficient implementation for the Muon optimizer. And these are some of the results that we presented in the paper. So as you can see, with the same number of parameters and the same number of training tokens, we just replace the original AdamW optimizer with the new Muon optimizer. It's going to improve the performance across the board significantly. But there was this new challenge that we encounter when we try to scale it up further. When we try to scale Muon for a 1 trillion parameter model, we encounter a new issue about training instability. So as you can see on the left figure, we observe that the max logits quickly explodes and quickly exceeds 1,000. And the typical values for training for this max logic is about, say, 50 or maybe less than 100. But for Muon, it quickly exceeds 1,000. And at the same time, we observe training divergence on the left-hand side. If you look at the training loss, it goes down a bit, but then at the end of the day, it explodes, and it cannot converge as expected. So this is one of the technical challenges that we have to address. And the solution to this is to introduce this new technique called QK clip. So basically, what it says is that for each attention head in this entire neural network, we're going to, in the forward pass, we're going to compute the max logit, and then we're going to calculate a dividing factor that can be applied to each key projection, as well as the query projection, so that we can sort of clip the maximum value of the query and the key to sort of constrain it into a given range, so that we're not going to have explosion anymore. So these are some of the empirical results. On the left-hand side, there are 2 curves, but they are strictly overlapped with each other. So these are the training curves before and after applying the clipping technique. So you can see the clipping technique does not affect the training loss decrease at all. But on the right-hand side, if we inspect the intermediate metric, if we inspect the max logit, it's going to be effectively constrained. So it first explodes as before, but at the value of 100, is going to be clipped at a constant value for a long time. And then after a certain number of steps, it will just naturally go down. So the neural network sort of find a way to constrain the maximum value of the max logit to ensure a stable training process. And at the same time, it doesn't affect the training convergence as shown in the left figure. So we employed this technique in our K2 model training and successfully scaled it to 1 trillion parameters. And this is the first example of a large-scale Muon training in the history of machine learning. And the second